all that analysis. So pay attention. Tell you, please.
Yes.
Let's take that.
Yeah, we got it.
Thank you.
Yeah, sì, potete lasciare, posso? Yes, yes, okay.
I assume all the slides and start back.
You
should find their.
Yeah. Much better.
Do you need guys here tonight? You see, we are the next last day, we already started 2 minutes late. We are getting so.
Makes sense. It gets tiring. Okay. All right. So yeah, so I'll talk about data analysis. And at least different sources of gravitational waves that maybe that you talked about in the first couple of weeks here. So my name is Andrew. I'm a postdoc at Nikhef in Utrecht. And so yeah, I'll talk about neutron stars and primordial black holes as well as dark matter. And it's very ambitious, but we'll see what I get through. And this will all be in the guise of long-lived signals. So long-lived means at least like thousands of seconds and up to forever. And so it's quite different than the signals that I guess Maria and I talked about in the first week. So let me advance. So this is my understanding of this workshop. So that people here are interested in applying QFT stuff to solving hard equations and post-Newtonian, post-Minkowskian self-force expansions, and the output is some waveforms for binary systems. But I just want to ask the question if there's other ways that we can think about other ways that we can apply QFT formalisms to other types of gravitational wave sources. So where the physics is also quite complicated. So for isolated neutron stars inside the star, as well as if there's some like dark matter cloud around a rotating black hole. And is there a way that we can think to apply these same techniques to the difficult equations that are also in that field, in those fields? That was just kind of my overview. And so let's talk about a few sources so I'll give some introduction and motivation, and I'll talk about some sources of long-lived gravitational waves, ones that come from bumpy neutron stars, ones that come from dark matter clouds around spinning black holes, ones that come from in-spiral neutron star systems, which are more relevant for future detectors when we can see low frequencies much better than we can see in LIGO and Virgo. And then I'll talk about some primordial black hole binaries and mini emeries, which are like ordinary emeries, but a different mass range that we can see in ground-based detectors. And then some direct detection of ultralight dark matter if there is time. So just some motivations. So I mentioned these continuous waves. So these are quite different than the sources of gravitational waves that come from the compact binaries that merge. These are signals that are essentially monochromatic, up to some deviation due to the relative motion of the Earth and the source, as well as essentially some intrinsic frequency change over time due to the emission of gravitational waves. And so this plot is supposed to show you the different frequency modulations that are relevant over different time scales. So you have the rotation of the Earth that modulates, say, I think it's like 100 hertz signal on the order of, I don't know, what this is like 10 millihertz maybe. And it's relevant on the time scale of days. Then you have the motion of the Earth around the sun. This modulates a signal coming from somewhere in the sky by maybe 5 millihertz. It's supposed to be bigger than this modulation. And then if you look on the time scale of years, what you see is that there's a trend downwards of the frequency as a function of time. And this comes directly from the gravitational wave emission from a bumpy neutron star. And these other modulations, these are just due to the fact that we have to observe these systems from a rotating, a frame of reference that's moving with respect to the source. So these are extrinsic frequency variations, and then this is the true frequency variation due to the emission of gravitational waves. And just like the binary systems were a major milestone. Oh, you have a question?
Yes, curiosity. So Neutron is not stuck on Earth, but will rotate around the sun.
Yeah.
Will also rotate on itself.
I don't know. I don't think so. I think the major evolution is the major Doppler shift is from the sun, orbiting the sun, but I'm not entirely sure. Yeah. Okay, and so just like the binary systems, a detection of these type of systems would be a major milestone in gravitational waves, and it would have the added benefit that we can keep observing them because binary systems, they merge and then they're gone. They don't emit any more gravitational waves. But for these type of sources, they really last forever, and so we can keep getting better estimations of parameters, and hopefully we can even learn new physics, or we can test new physics based on these observations. I'll explain it a little bit.
So this pulsar finding array detections don't fall into your category of continuous waves?
No, because they use pulsars, but they are looking for nanohertz gravitational waves that come from the in spiral of like supermassive black holes. And so they are continuous waves in the sense that they last a very long time, but the frequency range that they emit in is very low, like nanohertz. And so they fall into this category, except that so there are these modulations, but then this frequency drift is due to the in spiral. So it's like a very slow chirp up.
From the pulsars are the detector of
Yeah.
the sources.
Yeah, no, I'm just asking if they're not continuous waves in the way that you just defined.
No, they are continuous waves. It's just that their frequency shift is due to a slow in spiral. So it's as if you imagine the LIGO Virgo detections with these chirp signals. Imagine the chirp is basically flat. That's what the nanograph supermassive black holes are doing. They're basically almost fixed frequency sources, but there's so many of them, so they superimpose on each other. But as Ricardo said, the pulsars are the detector. They're not the source of gravitational waves. Yeah. Okay. And as I'll explain, also other binary systems that are in spiral, they can also give sources of continuous waves in an analogous way, as I've just described. Any other questions? All right, so this is just to give you an overview of the different types of sources of continuous waves. So I've mentioned these bumpy neutron stars. You can also have very light in spiraling primordial black holes. You can have ultralight dark matter that couples to the interferometers that gives rise to some signal that's like a continuous wave. You can have binary neutron star in spirals, which I'll talk about. Also stuff in LISA, like white dwarf binaries, intermediate mass black holes that are basically in spiraling forever. And because of the complexity of these sources, and because of the computational cost of doing match filtering, as I'll discuss later, people have had to develop a lot of different ways of doing these kinds of searches. And this is because match filtering is simply impractical for the kinds of sources that we look for, because they just simply last for a long time. And so there's methods, there are some match filtering where we know a lot about the source, but there's also machine learning based methods, as well as methods that come from particle physics, like transform, and these are just some pattern recognition techniques that are used to find tracks in the time frequency plane, and also cross correlation. And I'll talk a little bit about how we do the analysis shortly, but this is just
It's kind of the longest practical window of connection.
from my understanding, I think it's something like, at the moment, it's something like 500 seconds.
How many seconds?
500 seconds. Because we've thought about.
So even the one neutron star and spirals are, you're only actually going to look for part of the signal when you're recovering the spirals.
Yes, because for the very long in spirals, the phase mismatch between the templates just increases a lot with time. And so, so even for this, which I'll talk about, we don't do match filtering because the signal is simply too long. So there are other ways you can look for this stuff.
And you don't have templates that are going to be based coherent over long enough period of time.
So actually, we do a lot of these searches are not they're done in like the time frequency plane, where you really only care about the power, or you don't care about the phase. When you care about the power, you have a bit more flexibility in the kinds of templates in quotes that you could use. Any other questions? All right, so yeah, there's a bunch of different methods that have been designed to search for all these different types of sources. And they're mostly based on clever summing of stuff in time frequency plane. So now I'll talk about neutron stars, because this is kind of, I think, where this subfield started. So the idea is that there's a neutron star that has some bump on it, and this bump causes a deviation from spherical symmetry, and this bump essentially causes this time-dependent quadrupole moment, which radiates gravitational waves. And the physics is that the rotational energy, or the E dots of the neutron star, is transferred into gravitational waves, and then this causes the neutron star to spin down over time. That's why in the first slides you saw this behavior over long time scales. So now this spin down is extremely small. This is something on the order of 10 nanohertz per second. So we're talking about real signals that are very, very monochromatic, where the Doppler modulation, due to the fact that the Earth is moving with respect to the source, this gives you a larger frequency larger shift in frequency than the one that's actually intrinsic to the source. And so it is really the Doppler shift that makes searches for these unknown sources challenging. And this mountain could be sustained by some magnetic field that's on the inside, and this can support essentially a maximum deformation away from spherical symmetry. But these mountains are also very small. They could be like millimeter size or less. This is because the gravity of the neutron star is so strong that it's impossible to have any like major deviations from spherical symmetry.
So, I mean, in principle, the spin down in the pulsar, you could also see.
Yes.
And is there astrophysical evidence for this kind of?
Yeah, so I'll talk about this in a few slides, but yeah, so you can measure the period that P dot will go out from pulsars. And so if you from this information, you can calculate something called the breaking index. This is some quantity that tells you what is the physical emission mechanism of the source. So like n equals 3, this breaking index of 3 implies like a predominantly magnetic dipole emission. And then 5 is predominantly this like mountain emission. And then n equals 7 is something called R modes. And so these are toroidal perturbations on the surface of the neutron star. And so for some pulsars, the breaking index is close to 3. These would be electromagnetically dominated. But then there are some where the breaking index over long periods of time tends to 7, which would be R mode domination, which would be gravitational waves. So there are some pulsars that we know that are probably emitting gravitational waves that are the dominant contribution. And furthermore, we also know that pulsars glitch. And so glitching cannot be explained, I guess, primarily by magnetic emission. So there's probably some rearrangement of something on the surface or inside the star that causes this immense frequency increase or decrease over time. So it's something like a microhertz in a very short period of time, like a second, compared to the nanohertz per second that you get from the classic spin down. So this evidence, the glitches plus the measurements of the period-to-period derivative, they imply that there's some emission mechanism that cannot be entirely explained by a magnetic dipole emission. Yeah.
About the glitches, do people think they're due to starquakes?
Yeah, they could be. Yeah, the starquake is one model for them.
Because the earthquakes, they have some foreign dynamics that you cannot predict when they have.
Yeah.
But the statistical distribution is quite well studied.
For earthquakes.
For earthquakes.
Okay.
Yes. For starquakes, are there any similar studies? So,
I don't think so. I mean, I don't know. I mean, I think that it's just a very hard problem because we don't actually know that they're starquakes. We just observe the pulsar, the frequency just jumps. And some pulsars it jumps more frequently than others. And so I'm not sure that people have done like a science study about that.
So the fact that you have specific candidates, does that help you search?
Yes, a lot, because when you have these.
You know the relative timing that you're looking for between different variables.
Yeah. Yeah.
I guess you also know something about the modulation.
Yes, like the relative time is not so important because the signal is always is lasting forever. So you turn the detectors on, the signal is there.
But
And
obviously, because you're not looking at the phase conversion.
yeah, but in the actually when you do when you look for the pulses that you know exist, then you can do match filtering. So you can make this template. So then the phase is much more important thing. But since the signals they arrive, I mean, of course there is this delay where you observe the signal because the detectors are separated, but because when you turn the detectors on, the signal is there, it's hard to conceptualize what the delay means because you know the signal is always being emitted before and after the detector is on. So what is the concept of a time delay? Time delay makes sense if you have a fixed origin of a fixed emission time of the signal, and then so when detectors are off, turn them on, the gravitational waves take a finite time to get there.
I mean, actually, I don't quite understand because let's say you forget about noise and so you have two signals, and it's true that of course you can shift by a equal number of periods and you see that as the thing is modulating, then the relative phase is shifting, and that's something that.
Yeah, that's true. Yes, yes, you're right. I think that we can track that. It's just that this
I don't know
happens.
if it's practice.
Yeah, so I think in practice, since the signals last for such a long time, we look mostly at the integration time is much longer than this time shift, and so I don't think that we actually think about the relative phase in the detectors because we just essentially take a match filter of both data sets separately and then look if that frequency is the SNR and the frequency is high in both detectors. I don't think we think about the time delay like you think about in the binaries. All right, so yeah, I
So
can.
if we talk about the frequency, are the strains like large enough that you think people can detect?
Yes, we'll talk about this. So the strains are a few orders of magnitude weaker than the ones that come from binary mergers. But the gain here is that the signal lasts forever, so you integrate. And so you can basically get below the noise floor like a few orders of magnitude more than you can for the binaries that merge. And so this means that you can probe amplitudes on the order of 10 to the minus 25, 10 to the minus 26, which are like 3 to 4 orders of magnitude weaker than the ones that come from the binaries.
So when I look at these curves, these sensitivity curves from the interferometers, I should keep in mind that it's for very specific signals, or so the curves change depending on which signal I'm hunting for?
So the curves are fixed by the detector. So whatever the detector, whatever the sensitivity is at that given time. But what's important is how much below that curve you can go when you are integrating for a long time. So the curves that are made that way, they are essentially, I think the Fourier transform is fixed to something like hundreds of seconds and maybe even less. And so that curve just gives you the sensitivity of the detector. It tells you nothing about the source. And the sensitivity is related to the duration of the source, essentially by a square root of the observation time. So the more you can observe, the more below that curve that you can probe. And but that curve is in units of per hertz. And we think about the amplitude as being, in units of strain. So there's a conversion factor you need to do based not only on the observation time, but also on like the frequency that you're looking at. So, but those curves are fixed. Those curves are a detector. But like for the binaries, I think the strain should be above it because the signal is so short. But or at least like very close to it. But for these kind of systems, the strain can be very, very below, and you can still detect it. Although we haven't, but in principle we can. Any other questions? All right, so yeah, so it's just to give you an idea from the binary systems that the first one we detected had a strain of about 10 to the minus 21. And for a known pulsar, we have strains that are on the order of 10 to the minus 26, based on if we assume that all of the rotational energy is going into gravitational waves. And so the difference is that here, the signal lasts for 0.2 seconds, and here the signal lasts for 1 year. So naively, if you take the ratio of 1 year to 0.2 seconds, you can obtain roughly the improvement in sensitivity that you would get by integrating for a long time. So this is like 10 to the 7th second, this is 10 to the -1, so the ratio is 10 to the 8th, and this gets square rooted. So it's about a factor of 10 to the 4 that you can probe weaker than this signal, roughly speaking. And so this is just for a particular known pulsar. Obviously different pulsars, they're different distances away from us, and so they have different maximum strains that we could observe. But this motivates the need to integrate for long times, because the sensitivity scales with the square root of how much you integrate. So you can gain a lot just by looking at the same source for a long time. And so here, so then something else to keep in mind is like the physics of, okay, so what's causing this deformation, and can we actually, so what does it mean if the signal is so weak? And so unfortunately, we don't actually have a good prediction for what the minimum size of this mountain would be. Or if there is a prediction for this, it's probably depends on the equation of state. And that means that we quote limits for the things that we know in terms of how much of a weaker amplitude can we see compared to if we assume all of the rotational energy goes into gravitational waves. But for the sources that we don't know anything about, so we can't see them electromagnetically, we just have to keep digging into the noise. And we don't know if there's this minimum degree of deformation. We don't know if it's a universal thing or if it's equation of state dependence. So we can't say, okay, we'll detect something this run, or if we don't see something this run, then we have a problem. So we can't really make these kind of statements. And so unlike the case of the binary mergers, the signal models that we use for these types of sources are very simple. They're Taylor series, to first order.
So I'm a little bit confused about saying, why does there have to be a minimum degree of deformation?
I don't think there doesn't have to be. I mean, I think that there are some predictions based on, so for example, if you can calculate what is the minimum magnetic field that can exist inside the star, this would imply a minimum degree of deformation. So maybe there are some models that predict that
Say you can be a statistical question of the population of these systems.
Yeah, it can also be a statistical question. So it's unknown. I mean, people make predictions based on theory that there could be a minimum deformation. Maybe it comes from like maybe it comes from the fact that like when the star explodes, there is some conservation of magnetic flux, and so this can fix the magnetic field that could be inside the neutron star. But I don't know. I mean, I think that there are probably statistical arguments as well as physical arguments that are made about this degree of deformation. But I agree, there doesn't have to be one. We can just keep digging into the noise. It's just that we don't know if the neutron stars are just like super spherical, or if there's something that we're shooting for. That's the only thing. So the model is very simple, but the fact that we don't know a lot of parameters, so the fact that we don't know the sky location when we talk about searches for some unknown neutron stars, this makes match filtering impossible, because the number of sky points in a search that lasts 1 year would be something like 10 to the 17, 10 to the 18 points. You just can't do it at one frequency. We just can't do it. And so that's why you have to devise other ways of looking for these signals that are not based on match filtering. So now I just want to talk about like localization, because for the binary systems that we can't relocalize with one detector because the signal is too short. But for continuous waves, we can observe for as long as there is data. The Doppler shift, even though it makes the computational cost very high for unknown sources, the Doppler shift is what allows us to localize sources in the sky. So something like a degree of resolution, depending on how much time you integrate for and what frequency that you're looking at. And so So the idea is that within, you can calculate essentially what is the frequency shift induced by the Doppler. And this frequency shift is on the order of 10⁻⁴ hertz. And if you compare this to, if you observe for say 1 year, that means the spacing in the frequency domain is something like 10⁻⁷ hertz. And this bin width is much smaller than the Doppler frequency shift. So that means that where the source comes from on the sky, which is this n hat vector, dotted into the velocity of the Earth, this will be different for different sky locations. And so you can resolve this because your frequency bin size is so small. This one, because your observation time is so long. And so that's the power of these sort of searches, that we can actually localize things even with one detector. So we don't need to do triangulation. But in practice, we need to compromise between the cost to actually do these searches as well as how much resolution we want to have in the sky. Okay, so just talking about the neutron star stuff, we have basically 3 different categories. One is where we know everything about the sources. This is targeted. One is that we know where something is, but we don't know what its frequency and frequency derivative are. And there's also a third, which is the all sky, where we know nothing. And these are the most computationally heavy. These are the most sensitive because we know everything. These are something in between. And so I'll talk about these in turn. So in these searches that we know everything, we can do match filtering, because essentially astronomers give us what the frequency derivative, and the double dot of the frequency are. And then we can essentially we can demodulate the data, assuming a signal with these parameters, and point into the direction of the sky where the source is coming from. And that lets us do a match filter because we know everything. And so we basically take one Fourier transform of the data, and we look at the frequency we look at this frequency, or twice this frequency, because the gravitational wave is emitted twice the rotational frequency of the star. And then we hope there's a strong peak at that frequency. And
What about glitches?
yeah, so they affect it. So we try to remove them. But again, since the glitches occur on a very short time scale, and we integrate for a much longer time scale compared to glitches. So they certainly affect the noise floor. So we try to remove them, but they don't affect as much they affect the sensitivity to a bit, but it's not like in the binaries where if you have a glitch that lasts for 0.1 seconds and your signal is 100 seconds, this is a problem. But here the glitches will last for a fraction of a second, but the signal lasts for a year. So
No, I mean, the frequency changes afterwards, so you have to start over.
oh, you mean neutron star glitches?
Hmm?
You mean neutron star glitches?
Yes, yes.
Ah, I thought you meant glitches in the detector. Okay. Yeah.
No.
So in the case of in case of neutron star glitches, yeah. So what you do is you basically, so there are different approaches. One is that you just you know the time of the glitch, and then you take a Fourier transform before and after. You just ignore the glitch entirely, and that's one approach. So this is pretty good. I mean, in the sense that you don't lose much sensitivity, but then you kind of miss any kind of properties that could have been any kind of interesting physics that could have happened at the glitch. That's probably the most common way of dealing with the glitch, just ignoring it. And then I think that the other thing is that you can essentially put in a parameter in your model, which is some kind of phase offset that where you don't really know what it is, but it accounts for the change in the phase that results from the fact you have this glitch. And then you can do your analysis, and then I think you marginalize over this unknown phase. So in this way, it definitely affects your results. But it doesn't really tell you anything about the glitch. It just tells you that that there was a glitch there.
But if it's a pulsar that you're observing, you know when the glitch happens. Right?
Yes, you know when the glitch happened, but you don't.
You even know the change in frequency.
So yeah, on the size of the glitches, this is fine. But the glitch lasts a finite amount of time, say like maybe a second or something. And so in that second, you don't know what's happening because you can measure the frequency.
Cut out
That in practice, a lot of people just cut it out. See, they look at the time sequence around it, or they just include some parameter that they don't know, some phase offset, and then they marginalize over it. Because
it's not just phase; it's changing frequency.
they are only off by an integral. So yeah, the phase of the signal and the frequency of the signal are both changing, and And but we don't know necessarily how they're changing. You can measure the spike. But you don't know like what is the mechanism that's causing this increase in frequency, and so you can't model how the frequency is actually changing. And so that's why they have this arbitrary phase offset that they put in, or they just ignore it. Any other questions? All right, so then we have the category in between where we know the sky location, but we don't know none of the parameters. So if we look at the galactic center, for example, we know that there's neutron stars here that we can't see. So we know that there's like if you look at the supernova rates and then you look at the age of the galaxy, we can estimate that there's probably around 1 billion neutron stars in the galaxy, of which we see thousands of them. So we know that there's other neutron stars here that we can't see. So this motivates what are called more like blind searches, where we don't actually, so we don't rely on any kind of electromagnetic information to decide where we look. I mean, so we rely more on physics. It's okay that we know there's neutron stars in the galactic center. We think there are. We know that there have been supernova. I think these are supernova remnants, and so probably they left behind something. It could be a black hole, it could be a neutron star, but we're not sure. So then these kind of astrophysical targets, they motivate looking for something here, but we don't know anything about the frequency or the rate of change of the frequency, because we don't have any measurements of these things from astronomers in these particular sky locations. That means we divide other methods they're called semi-coherent. It means they divide the data into smaller chunks over which the power is combined with in each of these chunks without phase information. So I'll talk about that later. But so yeah, that's some kind of intermediate category. And then finally is the category where we know nothing, which is the most computationally expensive. It's also the least sensitive. And but these kind of structures are the best for finding any kind of new pulsars or new physics. And this is because the model that they use is very simple. It's just looking for, well, I mean, also in this case, the model is simple, but the searches that are designed for neutron stars that can come from anywhere in the sky, they take different approaches. Some based on models, some based on model independent. And so these can be quite sensitive to things we don't expect. And certainly because we're not relying on electromagnetic observations, we can in principle see things that we wouldn't expect. And so these are the most computationally expensive searches, but they are quite promising if we can actually see something. So now I'll just give you a brief overview of how we actually do the searches. So when we know everything, it's the match filtering. So that's kind of what people in the first week talked about. And when we don't know the source location or its parameters, or we're looking for some exotic physics that we don't really know how to model, we use what are called semi-coherent methods, where we break the data into chunks of particular length and time. So we call it TFFT. For each FFT, the signal power is contained to one frequency bin. This means that each Fourier transform, the signal is monochromatic. Because recall that we are looking for monochromatic things, and the optimal way to look for monochromatic things is a Fourier transform. We choose this length of the Fourier transform, so we choose the duration in which to divide the data. So the 1 year data, we divide into chunks of length 1,000 seconds. And we choose this length based on physics and based on the criteria that we want the signal to be monochromatic in each of these Fourier transforms. And then when we have the information, each of these chunks, we combine them. So we combine the power in each of these chunks without any phase. So this is why they're not as sensitive as match filter, because we lose the phase information when we do these kinds of searches. But the reason we have to do this is because match filtering is just too computationally heavy. And if there's any uncertainty in the signal model, which for neutron stars that we know that there could be uncertainty, we don't know the equation of state. And for exotic physics, these like dark matter clouds, we make assumptions, or we rely on theories that are good, but they may not capture all the physics that's happening. And so match filtering is not only too computationally heavy, but the models are too fixed. And if we it doesn't really allow for any deviations from the model. And so these type of searches allow you to find things you don't expect. And so they're robust towards, whether they can account for new physics that you don't expect, or old physics you don't expect. Okay, and so what do the results look like, just to give you an idea? So on the left-hand plot is a posterior. So on the y-axis is the posterior. On the top axis is this ellipticity, and which is the size of the mountain. And this is something that's related to ellipticity. It's the observable, but I don't have a good intuition for what the what it really means. I understand much more the ellipticity, and so the posterior is this curve, and so you see that it's peaked at 0, and this means that the preferred value of the ellipticity is 0. This means that we are not sensitive to gravitational waves that come from this particular source. This is for a known source, and the vertical lines correspond to the 95% upper limits from 3 different searches. And then the black line corresponds to the ellipticity that's predicted, assuming that all of the rotational energy goes into gravitational waves. And so you can see that.
So is this the particular source that has this L equals 7 dominance of the radiation of the pulsar?
L equals 7.
It was this toroidal mode.
I see. No, so this is a different source. It doesn't have the toroidal mode. This is a source that that probably we think is emitting gravitational waves predominantly, or at least the breaking index is not this index is not exactly 3. Maybe it's 3.5 or something, which implies that there's a mix of electromagnetic radiation and gravitational waves. And so this is a search for the mountains, not for the toroidal perturbations. We also do toroidal perturbations. And
No, I'm just wondering about the logic, because you think that this greatest likelihood of finding something would be the ones where it's actually dominated by radiation.
yeah, so we do look there. These searches are actually very cheap to do. So we pick hundreds of pulsars, and people pick hundreds of pulsars when they do the search for all of them. So for the toroidal perturbation one, yeah, we do a bunch of searches for that, and
But you didn't see
didn't see anything there. And but the other thing is the interplay between so okay, we know that things are emitting. We know that this index is set, so we think that the toroidal perturbations are dominating. But then there's the factor of how close is it and what's its rotational frequency, and these also affect the sensitivity. And so while yes, if everything were equal, then definitely gearing towards where we know that the index is close to 5 or 7 is definitely a good thing. But because of the interplay between distance and frequency, and distance and frequency, as well as this index, then the optimal search is where you can actually probe below this assumption that all the energy of rotation goes into gravitational waves. You have searches like this for millisecond pulsars where you are surpassing this limit. And so this interplay between distance and frequency and break index, they are all important in motivated searches.
So is this particular source one where you have, in some sense, the greatest sensitivity? Is that why you're showing?
Yeah, I mean, we're showing it because I'm showing it because it's the first time that we were able to get below this limits for a millisecond pulsar. So like we can predict the maximum mountain size, which is this black curve here for this pulsar, and we are probing mountains that are smaller than that. And that's the first time we could do it for these millisecond pulsars. That's why the plot is significant.
But in this particular one, you know that it cannot be a spin down because there's electromagnetic loss.
Yeah, but the logic
that's not taken into account in the black line.
So so the black line is assuming that all of it goes into gravitational waves.
Yes, so for this particular pulsar, if you subtract the part that is known to be electromagnetic, how does that shift this black line?
Yeah, so that's what we don't really know. I mean, the only thing we can say is that's okay, this is what we do, what we get if we assume you know, this spin down limit, all
We
the,
know that that assumption is wrong.
yes, we know it's wrong. So we do the search and then we find that we can probe mountain sizes that are smaller than that allowed by the maximum, that allowed by this.
No, but you can see that the black line should be shifted left somehow, take into account the.
Consider it as not bound.
It's upper bound.
I know, but the question is, the actual searches, right? Their significance is determined not by the black line, it's determined by where the black line should be if you took into account the known electromagnetic.
But we don't know this.
No, but you know that there's some balance of the different modes.
Yeah, so I mean, if you calculate this for the, assuming all energy goes into magnetic or electromagnetic radiation, then the ellipticity is 0. So this curve, this is the upper limit, and 0 is the lower limit.
No, but the thing is, you don't know that it's all. Right?
Yeah,
But you have some lower bound, presumably from the extreme mode.
I don't think we have a lower bound. Because we don't know what the fraction is that's being emitted. We just know that we're measuring something that's, you know, between this 3 and 5. And then we know that if we assume all that goes into gravitational waves, we get the black line. And then if we do the search, we get lines that are, we get smaller mountains. So therefore we can say that, okay, we can probe a regime where only like 1% of energy goes into gravitational waves. But that doesn't make any statement. That just means that so no more than 1% goes into gravitational waves. That means that at most 99% goes into electromagnetic radiation. But we can't. We don't have a theoretical prediction for what fraction goes into electromagnetic energy. So we can't put a lower. We can't put like another line on. Yeah, sorry, yeah, I think, yeah, it's just that we don't know this fraction. We don't know what fraction goes into gravitational, what fraction goes into electromagnetic radiation.
And what is the utility of the spectrum you were talking about earlier?
The spectrum.
Well, the different modes and breaking.
Yeah, so then this has to do with the physical thing that's being in, but the physical mechanism for the change in the energy of the neutron star. So one is that it's emitting electromagnetic radiation, and one is gravitational into gravitational waves. But this is based on, this is your pure physics. This has nothing to do with detection. And so the determine what sources are viable or good places to look, it also depends on gravitational frequency and the distance they are away from us.
Sure, you said that. But,
Yeah.
I mean, if you know the mass of the neutron star, you know something about its radius, you know how much energy has been lost as the frequencies change.
Yeah, I mean, we can measure that, but we don't know the mechanism for it.
But it's more that in a sense, I mean, to understand what the significance of the green and blue lines compared to the black line is, we'd like to know where the black line ought to be if you took into account, maybe even if it's somewhat model dependent, where the black line should be if you took into account the electromagnetic losses.
Yeah,
As you said, you should know the equation of phase, distribution of the radius, distribution of the mass.
yeah, we
don't
don't know.
have the information.
Yeah,
Just some bands instead of one.
yeah. I mean, there's like this line is definitely fixed. You know, there's just one value. But yeah, if you want to shift it, then there's a band that you can consider based on different equations of state. Perhaps if you could predict the amount of energy that should be going into electromagnetic radiation. But so all the plot shows is that no more than 1% goes into gravitational waves. So that's all we can say based on not assuming anything about the physics of the neutron star, aside from, yeah, we don't assume anything about the physics of the neutron stars. So it's a very different approach to the binary systems. The binaries, we know everything. You know, we don't need to make these kind of like arguments about, we don't need to make these kinds of, not hand-wavy arguments, but we know a lot more. And so we can put constraints in both directions. But with neutron stars, we don't know so much. And we have limitations also with how we do the searches. And so in some sense, the binaries are an easier problem because we know so much. They're just a computationally very expensive problem. But here we don't know a lot about neutron stars. All right. So it's been 50 minutes, I think, and I've only covered one source, so. So I guess,
You're not tired, we're not.
Yeah.
You're the chairman.
I'm not sure.
So if you're not tired,
okay, I mean, we can, until you guys get tired, we can talk.
And if people are watching this,
All right, so now I'll talk about gravitational waves that come from essentially dark matter clouds that could form around spinning black holes. So this is a super radiant process, and so essentially some quantum fluctuation would cause a dark matter particle to pop into existence near the black hole, and then this particle essentially gets scattered off the black hole and extracts energy and momentum. Energy and mass from the black hole. And this scattering only happens under a particular condition where the frequency of the angular frequency of the dark matter particle is less than the angular rotational frequency of the black hole. And in other words, I think that the wavelength of the particle has to be of the same order as the size of the black hole. And so what happens is that this cloud essentially builds up over time, not much time. As for ultralight dark matter, which for ultralight means something like 10 to the minus 13 EVs, at least in ground-based detectors. And so this happens. This super radiant process essentially builds up this cloud on a time scale that depends on the black hole mass, the product of the black hole mass and the boson mass, and the spin of the black hole. And so for these particular choices of parameters, for a black hole mass of 10, for this like gravitational fine structure constant of 0.1, for a spin of 1, you get something that takes like 27 days for the cloud to build up. But you should notice that this instability timescale is a strong function of this alpha. This alpha is essentially the black hole mass times the boson mass. And so, you change these things a little bit, you get vastly different instability timescales. And so it makes it hard to make general statements about, and you have to really make the statement of how long the cloud takes to build, vary specifically in different parts of the parameter space. There are different choices of black hole mass and boson mass. But for the parameter space that so for this parameter space, though, what we can say is that the time scale of the growth of this cloud is much less than something called the annihilation time scale. And so what happens is that the cloud builds, it stops growing, and when this condition is no longer satisfied, and then the bosons essentially will annihilate into gravitons, and they will emit, when they do this, they'll emit gravitational waves. And since the energy levels of this system are quantized, just like the hydrogen atom, the gravitational waves are emitted at each energy level, which means that they are at a fixed energy, so at a fixed frequency. And so these are essentially continuous gravitational waves, because the time scale for the annihilation process to finish is something on the order of 10,000 years compared to the growth of the cloud time scale, which is on the order of a month. And so this means a couple of things. First, that we can be reasonably sure that if a black hole has formed in the last, some number of 10,000 years, then these for sure will have clouds. And depending on the cloud, depending on the boson mass, certain black holes will have clouds and certain ones won't have clouds, because this condition has to be met. And this is a function of the black hole mass, the black hole spin, and then the boson mass. And so we can be reasonably sure that that if these systems do exist, they will be emitting gravitational waves in our lifetime. And so
this stuff is not degenerate to the black hole having some sort of accretion disk or something. I just want to know that.
Yeah, so this can complicate things. So in this case, we consider isolated black holes. And so I don't think there's an accretion disk for an isolated black hole, but I could be wrong. But in the case of a binary system of black holes, where people also think to look for these things, it must affect it, I mean. Or if it's a binary of a black hole and neutron star together and the black hole has the cloud, it's for sure will affect it. And we don't know how to deal with that. And there are some searches for like this kind of stuff for where one component's a black hole and the other one I think is something else like the sinus X1. So there's one black hole which is very, very highly spinning and there's another object. And there's for sure some accretion that's happening. And I think the conventional wisdom is just to ignore it and do the search anyway. But because we just can't model it. And this is like the kind of the practical approach because there are certainly models, there probably are models for this, but you want to design a search that's kind of robust against changes in the models of, for example, how the accretion could be happening.
I just say dark matter, but it can be any scalar that has the right quantum wave. It doesn't need to be dark matter.
I think so, yeah. It also has to be a boson. Because there has to be no limit on the number of bosons in a particular energy state. That's what makes the cloud so big. When there's like 10 to the 50 particles that exist in the cloud. Any other questions? All right, so that's kind of how, and then as I mentioned the quasi nature. So the cloud will, as it's emitting gravitational waves, it will get smaller, it will contract. And that's where the quasi nature comes from. So this system comes from somewhere in the sky, and it's emitting a gravitational wave that's almost monochromatic. So it's just like the neutron stars that I was just talking about, except that this contraction, which is a classical thing, it will cause us a positive rate of change in the frequency over time instead of a negative one. And that can be used to distinguish the two objects. Although also neutron stars can spin up as well if they're accreting from a companion, but
so this is a slow process when it's spin down the black hole in a way that you can measure.
can we measure the spins of black holes that are isolated?
Yeah, well, you said that there's a signal that's highly spinning, so you can measure it somehow.
Yeah, but I think that's, if I remember correctly, the measurement is something like greater than 0.999 of the spin of the sinus X1. So I don't know how I don't know what like accuracy and precision that you need to be able to have in spin measurements such that you could then predict how much this would be spinning down the black hole and you'd be able to measure it. But in principle, I think so. But I just don't know if in practice they can actually do it. And also we also consider the isolated ones. In this case, we can't measure the spin or if the black holes will merge, if there are two black holes merge into another one, then we have measurement of the spin, so we can predict what this system will do, what will happen with the boson cloud, but we can't, but I think for existing systems, we can't, if we don't see it, the gravitational waves, we don't see some merger, then we can't really measure the spin of an isolated one. It's another hard problem, right? It's a very hard problem. All right, so the signal, okay, I think I will just some practicalities. So the frequency is fixed by the boson mass, and there's some correction due to the fact that the cloud is existing in like the potential well of the black hole, but it's a very small one. And then there's some frequency drift that's also very small. It's also a very extreme function of the black hole mass and the boson mass. It's like the 17th power. And so it's very, it's very variable based on the boson mass. And so, yeah, I'll just tell you, I guess, what some results look like. So when we do searches for these systems that are isolated anyway, we essentially constrain a given distance away if there could have been a boson cloud that with a certain mass formed on a black hole with a different mass. And that's what you see here. Plotted is a boson mass on the y-axis, the black hole mass on the x-axis, and the colors correspond to different ages. So if the system is older, then the gravitational waves that come from it will be weaker because the amplitude falls off with some factor like 1/1 plus the age of the system. and to some power. And so yeah, so you see here the younger, so the way these plots should be read is that so the older systems are plotted on top of the younger ones. So the younger ones, they have the biggest constraint on this this plane. And then the older ones, you have only smaller, you have exclusion regions that are smaller. And so yeah, that's one thing we can do, which is pretty model independent. We just say, okay, that we follow the equations and we get this. And if we want to do something a bit more astrophysically motivated, then we can say, okay, we're going to assume some distribution of black hole masses and assume some distribution of black hole spins. We can sample from this distribution and then calculate basically calculate what the amplitudes of these systems would be, and we can determine if those amplitudes are detectable or not in our search. Where detectable means that these amplitudes have to be bigger than the minimum one that we can see at some confidence level. And so this comes from the search. This is just a number as a function of frequency. And this H naught, this comes from the fact that you can basically predict what the H naught will be for a black hole with this spin, with this mass, etc. And so here you get essentially an expression for distance reached in kiloparsecs as a function of the boson mass. And you have different curves that correspond to different ages. And you see this kind of behavior where they basically peak at some boson mass and they fall off. This comes from some interplay of these equations where you have this these alphas that go to some very high power. So you have a lot of things going on in there of the equations that give you this distribution where you're optimally sensitive to this boson mass for this, assuming this range of black hole masses. So you can see that we can see things, on the order of hundreds of kiloparsecs. So kind of a bit beyond our galaxy, but we are really probing stuff that's within our galaxy. Okay, so now I'll talk about inspiraling binaries, which I guess is more familiar. But now I'll talk about in the context of in the future detectors where signals last longer. So just to give you an idea, if depending on what is the minimum frequency that we can actually observe in the future detector, so if it's like 1 hertz, yeah, go ahead.
Can you go out to the exclusion plan?
Exclusion?
Yeah.
Yeah.
So the masses that are out here for the boson are like in between these quantities.
I'm sorry.
The masses that are still around that are not ruled out, these guys are between.
The ones that are not ruled out are the ones in white. The combinations
Oh, the one that is
outside the contours, yeah. They're the ones that aren't ruled out.
and well, I guess the one of the most delicious of this is that particles is the axiom. It is
Yes.
agree with the
Yeah, because these are axion clouds. It could be the axion that just forms around the black hole. These clouds. So yeah, it could be the axion. It could be the dark photon if it's a vector. It could be something else if it's a tensor. So
it's not intention with the just.
no, I don't think so. I mean, it's kind of like if the axion exists. So if it is of this mass, it will form around. This will happen. Like that, there will be black holes where this cloud can form. So it's kind of a consequence of the existence of the dark matter particle, I suppose. Yeah.
You also need highly spinning black hole.
Yeah.
We don't really know this.
Yeah, we don't know. So you also need high spinning black hole. This is for a fixed spin. So this is, I think, 0.9. And then yeah, these exclusion regions will shrink depending on what the spin of the black hole is. If it's lower, certainly they get a lot smaller.
Yes, but for energy, you have a bias information to see the black hole that having values. And anyway, the speed is not measured anyway. You won't as well. You don't know how it is.
No, I mean like we can get a nice week with that whole after from where.
Okay, yeah, but again, that's a very specific channel.
Yeah. And for these.
For those discrete, we know it's 0.7.
Yeah, so yeah, we know this, but then for these, like as I showed in the slide, the distance reach for this kind of search is around the order of hundreds of kiloparsecs. And we observe black holes merging in gigaparsecs or megaparsecs. So at least for the scalars, we can't reach them.
But the fact that you mentioned this black hole spin greater than 0.999, the fact that it exists, doesn't it exclude some of these bosons then? Because they would have spun down.
Probably, yeah. I don't know. Yeah, I don't know. I haven't looked into it, but
There's been seen that one.
Well, he mentioned that there's a black hole where the spin parameter is supposed to be greater than 0.999.
yeah, that's like sinus x1. That's like the official number.
I thought the upper part was huge, but say that it's 0.999 and
Yeah.
we trust the third, then I would have thought that it excludes some of these bosons.
It probably does, but like that black hole is a certain mass, so it would exclude essentially one line on this plot.
Sure.
Yeah.
But still,
But still, yeah. But still, yeah. So
people build these experiments to throw needle in the haystack of the
Yeah.
to see the action.
I also think that black hole is like maybe like a order of a solar mass. So we're looking for systems with we put the constraint between 5 solar masses and 100 solar masses. So like we wouldn't the gravitational relation with sinus x1 means that since the mass is so low, and since these signals are very strong functions of the mass of the black hole, we probably wouldn't be able to detect it. So we don't look for those like very small mass systems. But yes, there would be a constraint. I mean, somewhere over here, eliminating those on that particular mass.
I understand you wouldn't see gravitational waves, but you would be able to say something about the bosons.
Yeah. Yeah, no, I think you're right. I think you can. Any other questions? Okay, so let's move on to these inspiraling systems. So the idea is that so this is for binary neutron stars, but it could be any kind of compact object. So if you can, so the reason why signals are so short in LIGO and Virgo is because the minimum frequency that we can actually see something is something like 20 hertz or 10 hertz. And so when you do these match filters, you essentially start your analysis at like 20 hertz and you look for the frequency evolution up to say like 2000 hertz. And so this fixes the duration of the signal to be for black holes something like tenths of seconds, and for neutron stars something like hundreds of seconds. But in the future, when we have more sensitive interferometers like Einstein Telescope in Europe or Cosmic Explorer in the US, then the frequency floors, so the minimum frequency that we can see in these detectors will be something like 5 hertz or 2 hertz, ideally. And this means that the signal will last, some orders of magnitude longer in these detectors. That means that has a couple of implications. Bless you. That has a couple of implications. One is that the assumptions that are made in match filtering analyses, so that there's no gaps, that the noise is stationary, the noise is kind of Gaussian, that there are no glitches, all of this stuff starts to break down because you're observing for a much longer time now. And so you will likely encounter a glitch, or a detector might turn off, or there might just be some bad data at a certain time where your signal is. And so this is quite problematic. And additionally, the match filtering works by placing these templates in different parts of the parameter space with spacing that's based on the mismatch in phase between 2 adjacent templates. But since the templates will be longer in these future detectors, you'll need more and more templates for these long-lived signals, and that will be very computationally heavy. And this is a problem.
Why can't you just use, let's say, the 200-second long match filter for detection? And then you invest the computational energy to actually do the measurement.
I think you probably can do this. I mean, it just means that you're not using this low frequency sensitivity part to enhance so it limits your distance reach. You get a lot of sensitivity from the low frequency because it spends many cycles at low frequency. Although the amplitude is lower because it scales with the frequency to some power, so there's an interplay. So there's probably like an optimal frequency to start your match filter at, such that you gain some of the low frequency sensitivity, but your computational cost doesn't explode. So plus you lose localization, and people care a lot about this multi-messenger astronomy. So this being able to identify where in the sky transforms can merge before they merge, and that will come from the low frequency part. So this kind of discussion, this motivates the application of methods that we use to look for neutron stars and for these boson clouds around black holes. Like motivates the use of them for this particular problem. So applying them to look for these inspiraling signals. And if we are able to do this, then we can provide early warning, we can provide sky localization, and we could also deal with something that's called overlapping signals, which is essentially coming from the fact that we expect so many binaries to be visible every year. And so any given chunk of time, you're likely to have multiple signals that are happening at the same time in the same frequencies, or at least overlapping a bit. And so at the moment, match filtering can't really deal with that. Match filtering can deal with maybe like two happening at the same time. But you sacrifice some sensitivity because you like either you ignore one and you just do the match filter and the parameter estimation on the other, and then your other signal becomes part of your background, and then your background gets elevated because of the presence of the signal, and then your significance goes down, and that's why the sensitivity is worse. You could also just try to fit them both at the same time, but then you don't know how many you're fitting in practice, and you have a 30-dimensional parameter space instead of like 15-dimensional parameter space because you have the two systems that are merging. So there are problems, and I don't think we know how to deal with them yet, and so people are working a lot on this. Okay, and this is just an example of a frequency versus time map with an injected neutron star in spiral. So where the color is something like the ratio of the signal power to the background noise estimation. Okay. So I think I explained this about connection to early warnings. So I will just say that the types of systems that we talked about like monochromatic signals, but from binaries they will not be monochromatic, or at least the masses that we are interested in the future. So they will essentially be the post-Newtonian expansions, like that's how you deal with the in-spiral. And for us at the moment, from the continuous wave side, we're only dealing at the moment with the zero order PM. So we neglect the higher orders because this is the primary contribution to the frequency evolution over time. Although we do plan to extend it to the higher orders, but just in the beginning, this is what we've done so far. And so this equation is not actually monochromatic. So you integrate this, you get some function of frequency that's like a power law, and excuse me, and so but we have methods that can deal with that. We can look for these look for these kinds of tracks that are power laws in time frequency domain, and so here's just an example of one method that's based on the Huff transform, which is a method that essentially maps lines, points in one plane to lines in the other. Another way you can think about this is you essentially, so let me explain what the plots are first, and then I'll explain how it works. So this is a frequency versus time map with signals that you can see by eye, they're quite strong, and they're all happening essentially at the same time. And then you have another picture here, which is the chart mass versus the frequency. And the color is something like your SNR, your signal to noise ratio. And so this is taking, so that's what's here. And so to go from here to here, you do something that's called a transform, where you essentially integrate over time here, integrating along different curves. where you basically sample, you loop over all the possible different curves in this space, and you map them to a different space, which is this one. And where you see the small lights here, these are concentrations of signal power, which correspond to the parameters of each of these curves. So time and frequency points in the detector are mapped to frequency and chirp mass in the source. And so we can do this for now. But of course, there's a reduction in sensitivity because you get a signal that's here, it's like hardly there. You know, of course, it's I think it's you see that it's quite weak, like hardly visible here. So you have some reduction in sensitivity, but in principle, this method can deal with some number of overlapping signals and not suffer too much in terms of sensitivity loss. Okay, and I will just, I can skip this, I'll just say that these methods don't actually lose much compared to match filtering because of the practical aspects of the search where you have a fixed number of outliers, you can't follow up everything. And so at the neutron star masses, the sensitivity loss is around a factor of 4 or 5. But this really is dependent on how the search is conducted. And so this factor could in principle be less. So while we're not doing match filtering, you know, we certainly can not lose too much sensitivity. And then also just to give some sense of early warning. So depending on the chirp mass of the system and how far away it is. So here, this is the time you would have to warn astronomers as a function of the chirp mass of the inspiring system. And the colors correspond to different distances. And you can see that if the system is close, like 40 megaparsecs, like GW 17817, whose chirp mass was somewhere around here, we'd have, I know, a maximum a couple hours to warn astronomers that this system would be somewhere in the sky. And so now the sky localization is a bit trickier because if you recall, in this equation, this is the dominant contribution to the frequency, and the Doppler shift is, you know, something like 10 to the minus 4 times the frequency. So the Doppler shift is much smaller than this frequency shift over time, and that means that in order to get good sky localization, you actually have to detect something, then remove the modulation that's induced by this, so that the residual modulation is the higher order terms plus the Doppler. And then you can start to, if you could do this, which we haven't been able to do yet, if you do this, you can start to get sky localization on the order of like 10 square degrees for like a GW 170817 like system. So it's very much a work in progress. Just to give you a sense of, you know, what I guess people in data analysis are doing for the future.
Yes.
Yeah.
I love that we talk about this case of stuff. In the case of multivariate detection, see it's primarily in T and then does this picture change qualitatively or is it more or less?
I think that in terms of sky localization or early warning, you mean?
No, I mean your detection of some spiral phasing in T and then you detect and key guy yes, and then will be
Yeah, but I think that for ET and LIGO, there's not a huge difference in the time. It's like if you have like Lisa and yeah, I think that's the major thing is that the ET and LIGO are too close in frequency range. So the multi-band, if you have like this yeah, it's more for Lisa. Any other questions? Okay, so now I'll talk about light primordial black holes. I could also, I'll talk about light primordial black holes. So I'll just skip this background, but they're motivated by the fact that we're measuring a lot of low spins for black holes that have come from LIGO and Virgo. So people care now that these primordial black holes are not ruled out. So people are very excited about this. And depending on what so if they do exist, then they could take on a wide range of masses. And so each of the masses is, I guess, is predicted by some theory. And But each of these systems, that they form binaries, depending on their mass, they'll have very different signatures in the vector. And so just to give some more background, so a lot of gravitational wave efforts, they focus on detecting primordial black holes in the so-called subsolar mass regime, which is on the order of 0.1 solar mass systems. And so, and there's a lot of reasons for this. One is because the match filtering is like, you can kind of do it. I mean, the signals aren't too long, but you definitely are, I think you're restricting a lot the frequency range when you do these searches. But that's okay, because you can still make interesting statements about essentially what fraction of dark matter that primordial black holes compose. And so here, that's on the y-axis, this actually this fraction, this percent of dark matter that primordial black holes could compose as a function of a primordial black hole mass. And you see here the different colors correspond to different observing runs, data for different observing runs. And so, okay, you see that the constraints get better. I don't know actually why the orange ones are not as good as the 0102 HMR. I don't know what HMR means, but anyway, the point is that just to show that these are actually quite good constraints, and they come, and so they are probing a physically relevant regime where not all of dark matter can be explained by primordial black holes. And so that's been the focus, at least of LIGO and Virgo, as well as people who are outside of the collaborations. But gravitational waves from primordial black holes with lower masses, so like planet masses or like asteroid masses, they haven't really been searched for a few reasons. One is the fact that match filtering is just very challenging in this regime because the signals are lasting a very long time. And the other is that the signals that come from this, these kind of very light systems, they would be a lot weaker. And so that means so just like in the case of neutron stars, your sensitivity, your distance reaches very limited, and that's on the order of kiloparsecs compared to the mergers, which are on the order of megaparsecs or gigaparsecs. So that's probably motivated why people haven't really cared so much about lower mass. But from the perspective of people that work on these longer-lived signals, when these masses are so light, they resemble the continuous gravitational waves because they in-spiral for a very long time. And so this kind of thinking has applications not just for the primordial black holes, but as I showed for the neutron star spirals, as well as for any kind of long-lived signals that we may see in future detectors. And so let me just give some more motivation that this is okay. This is kind of like some plots of different constraints on this fraction of dark matter primordial black holes can compose as a function of the primordial black hole mass. And you can see that the gravitational wave ones mostly focus on the order 0.1 solar masses, which is this purple one. Microlensing has a quite big spread. And so, but this mass range here is quite unconstrained. And also these constraints can be avoided if you allow primordial black holes to form in clusters, for example. These constraints rely, I think, on isolated primordial black holes. And so even these kind of plots you should take with a few grains of salt, because there's some modeling assumptions that are going into making these plots. So it motivates the need to look at other so I think I will just skip this because it's not that interesting and focus on, I think, what we could do with them in the future. So if we can say in the future with LIGO, with a future advanced LIGO, and as well as with Einstein telescope, we can essentially make constraints in this mass region on this FPBH that are well below 1, which is this black line here, and the masses of 10 to minus 3, 10 to minus 4, 10 to minus 5, and the different colors correspond to different distances away from us, and at a fixed frequency. And so you can see if there are stuff in the solar system, we are quite sensitive to that. And if there's stuff at the level of the galaxy, and we can that are higher chirp masses, then yeah, we can constrain to like 1% of dark matter that could be comprising primordial black holes. So just to give a snapshot of what we hope to do.
This slide roughly mirrors the, our times proposing the previous thing showing existing limits.
Oh, I see. So, okay, so these limits, so the mass range of the limits would be here, something like here. But these limits don't apply to primordial black holes if they form in clusters.
So, okay, next cluster is the probably not inside the solar system.
Probably, so like,
that,
so I mean, it's more of like, I mean, you should think more, the solar system is probably a bit of a lofty argument, but at the level of the galaxy, we could see them, here.
so they don't apply at all, the curves just go up.
I don't know, I think that my understanding is they don't apply at all, but I don't know, I don't know the specifics of how these curves are generated.
Otherwise, I mean, if you take this curve at face value, it cuts a very significant part of the
Yeah.
sensitivity range out.
But you can take it at face value because it relies on modeling assumptions of primordial black holes. And so this can be avoided if they
I
form.
mean, it's a good thing to do the search one way or the other.
Yeah.
I'm not disputing that.
Yeah. No, I understand. So yeah, it's just that you have to be careful when interpreting these plots because it looks like the space is constrained, but only under certain assumptions. And whereas like the constraints here, they're only assuming that primordial black holes could form binaries. And so yeah. Okay, so actually I'll talk about this is more or less the same, so I'll just skip over some major parts of this, but just to say that we could also look for mini MREs and LIGO. So these would be systems with 10 solar mass primary object and an exotic companion. So like 10 solar masses with a 10 to the minus 3 solar mass thing. And so you can see this is a plot of the ISCO frequency as a function of the mass, the primary mass.
Ground board.
Could be like a primordial black hole, could be some exotic quark star. I don't know. It could be, there's many different things. This could be the exotic, quark boson star, primordial black hole.
Right, because it has to be exotic. It can't be just.
I don't know. I don't think. I mean, we just care about the mass. So I mean, if you can think, if there's something that's like 10 to the minus 3 solar masses, and then could, in principle, be bound to a heavier object, then in principle we would also be sensitive. We would also be sensitive to that. I don't know if brown dwarfs are that mass, are they? I don't know. We frame it in terms of exotic objects. I think probably politically because it just sounds cooler. But in principle, it's just a mass. So this 10 solar mass object with an exotic compact object of like 10 to the minus 3. But we only care about the masses. So we don't care what's the physical reason why this thing formed with that mass. But the implication is that you have a system that's like it's asymmetric mass ratio. So there's corrections to this post-Newtonian like PN0 that we've been using so far. So this could be quite big actually. I think I'll just show what the signal looks like. So we expect that the signal is basically divided into 2 parts. One is like the in-spiral part, which would be like the CW, and then one is the plunge. And we basically only think about the in-spiral part because this is the long-lasting one. It's the one that is most like the CW, and the plunge. Okay, we probably match filtering will be a much better way of dealing with the shorter signal that's plunging. And this purple line is just, I think, at the time when there could be some tidal disruption of one of the objects by the other. And the different colors, this is like the amplitude of the signal, more or less. And this is the frequency. So this is tracking how the amplitude changes with time, and the red dots show you essentially that, okay, it's 10 years from merger, it's 1 year from merger, it's 100 hours from merger, 1 hour from merger, etc. And then when you account for the spins of the black holes, which we hadn't done at all in the previous works, you get quite deviations at the level of the plunge. But moreover, I'll just skip this too, and I will skip that as well. But moreover, you have some modifications to this F dots. and which are a function of frequency as well as the black hole spin. And so then this affects the kind of searches that we can do. So here is on the y-axis the time remained to ISCO as a function of the frequency on the x-axis for a particular system. And so you can see around the things based on the different colors, different spins. And then this blue line is just the setting the CF term equal to 1. And so they insert the pure spiral case, no additional complications. And so you can see that there's deviations for the different spins at around, say, like 100 hertz. And so that's where we have to really consider how the methods that we're using or the waveforms that we're generating have to change in response to this difference in spin. And we're not even considering eccentricity yet. So I mean, this is very work in progress. And so yeah, just to give a sense of how far we can see these things. So these are on the order of, at best, like megaparsecs. This is the mass ratio on the x-axis. This is the distance reached on the y-axis. And the color is the amplitude, but it makes more sense to think about the distance. So you can see at these higher mass ratios, we can see megaparsecs, and the lower ones we can see on the order of kiloparsecs. And these, the higher mass ratios, I think they are much more, they're more transient, and at the lower mass ratios, they're more like continuous. And so it's also something that we have to consider. Okay, I think people maybe are tired, or I don't know.
I'd like to hear about the representation.
Okay. All right. Okay.
Just a mention that these ground dwarfs, they are further taken -2 solar masses.
So they were small round one.
No, he was talking about 10 to -5. That's not.
But 10 to the -3.
Originally 10 minus 3, but there are 10 minus 5.
10 to -2 this time.
Oh, the ground dwarfs.
Yeah.
Oh, okay. So in principle, yeah.
Something is not quite a very big Jupiter.
Yeah, like a big Jupiter. Yeah.
So,
Yeah.
times the size, the mass.
So yeah, like in principle, we could fine tune the search to look for specific mass ratios that would then say, okay, you have a 10 solar mass object with a brown dwarf like thing, or like an exotic object, or whatever. Because for us, really what matters is the chart mass, because from the chart mass we can construct any system that we want, as long as the chart mass remains the same. So equal mass could be like asymmetric mass, and so the only thing that changes are these like higher order.
With an exotic object, to me, it sounds a little bit like second order speculation. You know, but with
Yeah.
ground dwarf, at least you're just speculating about the existing system when you know the objects.
Yeah. No, I think, yeah, I don't know, I think it's just like a choice of how to market it. So you say, okay, like maybe people care about primordial black holes, so we'll say, okay, exotic object. But we say, okay, talking about astronomers, okay, maybe they care more about brown dwarfs. It's okay, we can detect brown dwarfs with this method. I think it's just fun. I mean, because it's really just the mass. But we don't, like, from this point of view, we do the search for the different systems, different mass, and then we interpret them later in terms of the physical things that they could be. And so it's very agnostic to what could actually cause these masses in the first place. All right, so now we'll actually shift away from gravitational waves and we'll talk about just dark matter. So this is not gravitational waves, like it's not a gravitational wave signal. It is essentially a correlated. It looks like correlated noise, and so I'll explain this a bit. So again, we're talking about ultralight dark matter, and depending on what is the model you have for the ultralight dark matter, this ultralight dark matter could couple to different components of the interferometers in different ways. And so let's take an example of a vector boson, the dark photon. And so actually, I will just say for all types of ultralight dark matter, we essentially treat this dark matter as like a superposition of plane waves. So you have like essentially a huge occupation number of dark matter particles in a given volume of space. And this means that you can treat all of these particles who can also be thought of as waves as a superposition of these plane waves. And each of these plane waves has a slightly different frequency because each of these dark matter particles is traveling with a different speed in this wave packet. And the speed is something like 220 kilometers per second, which is the velocity that the dark matter orbits the center of the galaxy. And so then there are small deviations in the frequency of the waves based on the distribution of the velocities that each of these particles will follow. And so this essentially means that since there's this finite velocity, this implies a time over which the wave is coherent. And that's given by this time here, which is under 14,000 seconds for a dark matter mass of 10⁻12 eVs. And so this also tells you something about the frequency shift that's induced by the dark matter. So the frequency shift is on the order of 10⁻6 and times the frequency in hertz. And this is actually even a more narrow band thing than the continuous waves from neutron stars. So this is really, really monochromatic. And so we basically look for a monochromatic line in both detectors that are spatially separated. And so this is actually quite hard because, you know, there's a lot of monochromatic lines in the data, and even ones that are correlated. And so it's kind of a hard thing to find correlated lines due to a dark matter particle and non-correlated lines, which is something else in the detector. And so just to give some, but what we can do is we can use the fact that there's this fixed coherence time. So within this coherence time, the wave essentially acts as if it has one frequency. If you observe for longer than this coherence time, then you can start to resolve these frequency modulations that are on the order of 10⁻6 times the frequency. And this won't happen for noise lines that appear in the detector. And so this applies to all types of ultralight dark matter that could interact with the detector. And so now I'll talk about some specific ones. So one is called the dark photon. It could couple to baryons or barium isotope number. And in the case of interferometers, this dark photons will couple to the baryons in the mirrors of the two arms of the detector. So, and because each of the mirrors exists in a different place with respect to the incoming dark matter field, the mirrors will actually move in a different way. And that means that this causes the laser to take a longer time going down one arm than another. And thus there's a differential strain that arises from essentially spatial gradients in the dark photon fields. And so that means we can think about using our detectors to look for dark matter that could couple to the mirrors and couple to the baryons or barium isotope number in the mirrors. And so they couple with some strength, we call it epsilon. This is essentially the fractional coupling strength compared to the electromagnetic coupling. So this is on the order of 10⁻23. It's very, very weak. And so we look for this stuff, and we use like a cross correlation method, and we try to essentially look in chunks of data that are of equal to coherence time, because we know the signals will be monochromatic in this coherence time, and then we stack the different Fourier transforms that we do over the whole year. And we can essentially get a result where we have the coupling strength on the, so we don't see anything, unfortunately. And we get a result that's something. What? Spoiler. I mean, I think if we saw something, we'd have to be very concerned, because then we have to justify it. It's like not correlated noise. I think that'd be really hard to do. But anyway, yeah, so we don't see anything. And so we can constrain the coupling strength, which is now squared, as a function of the frequency of the mass. And so you see here existing experiments, these are green ones and the purple one. And you can see the constraints that come from LIGO. They are the red and then this black and blue ones. And so you can see that above, say, like 80 hertz, that we are placing constraints that are orders of magnitude better on this for this particular dark matter model of coupling to the baryons in the mirrors. So that's pretty good. I mean, LIGO wasn't designed for this, and so we can still place very good constraints. And so that's just like one type of dark matter. Other dark matter could also couple to the interferometer and be visible in different ways. So I will just talk about, I think, a couple. Just the dilaton. It will couple to electrons and And it will alter the size of the beam splitter, which means that the light that comes back from the end mirrors, it will traverse different paths, different paths along this beam splitter, and that will give rise to differential strain. So you can also constrain this. That's what this plot is showing here, which there's a lot going on. So I won't really talk about it. But this is physically what's happening is that this dark matter particle is coupling to some standard model particle in the beam splitter, and it's the electron mass and the atomic Bohr radius are changing. They're oscillating in time, and that causes a physical change in the size of objects, and also the index of refraction of solids. And then because the light from each of the arms will take a different amount of time to go over, will cover different distances at the beam splitter, you have a differential strain. You have something that's in principle detectable. And so that's one way that another type of dark matter that we can probe with the interferometers. But essentially the searches are all the same. I mean, you just do the search for something that's monochromatic, and then you can interpret your results in terms of these different types of dark matter models. And finally, I'll just talk about the axions because they're very popular. So axions will actually modulate the polarizations of the photons that are going down into the arms, and will cause the left and right circularly polarized, the speeds of the left and right circularly polarized lights to be different depending on the coupling constant of the axion to photon, as well as the mass of the axion, etc. And so I think you need to install like a particular thing in the detector to actually be sensitive to this effect, but this doesn't really change this doesn't change the sensitivity towards gravitational waves. And it has the added benefit that you don't need to have like a strong magnetic field, where all these like many experiments look for axions, they throw a photon into a strong magnetic field and then hopefully it converts to an axion and then back to a photon. But in this case, you don't need a magnetic field. You just need the axion to couple to a photon, which will change the polarization, the velocity different polarizations of light. So that's actually pretty cool because you don't need this huge magnetic field. And I think that's basically it. If you have any questions, yeah, please talk after. And thanks for listening for 2 hours. Yeah, I think that's pretty much. Yeah.
You're around.
Yeah, I'm around. Okay, thank you.
Defense,